Now, in the 10th question, the power output of uranium-235 reactor, if it takes 30 days to use up 2 kg of fuel, and if each fission gives 185 million electron volt of that is usable energy. So, number of atoms in 2 kg we have to find. We have to use the mole concept as it is shown. So, in 2 kg of uranium, the total number of atoms by using mole concept is 5.12 into 10 to the power 24. Now fission rate, that is we divide this number by the time. So it is 5.12 into 10 to the power 24 divided by 30 days. So 30 days means 30 multiplied by 24 multiplied by 3600, that is 6 into 60. And the fission rate has become 1.975 10 to the power 18 per second. The usable energy per fission 185. So we know the total number of fissions. So power output will be 185 into 10 to the power 6 multiplied by 1.975 10 to the power 18, and to convert it to, that is watts, we multiply by 1.6 10 to the power minus 19, and it will become 58.4 10 to the power 6 watts, and the aggregate result will become 46 megawatt. Now in the 11th question, on disintegration of one atom, that is uranium-235 atom is disintegrated, the amount of energy obtained is 200 MeV, that is per atom. The power obtained in reactor is 1000 kilowatt. Atoms disintegrated per second. So we have to estimate the number of atoms disintegrated per second in the reactor and the decay in mass per hour, how much it will be. So to solve this question, power is known to us, 1000 kilowatt. And first of all, we convert it to watts by multiplying by 1000. It will become 10,000, that is 10 to the power 6 watts. And 1 watt is 1 joule per second. So it will become 10 to the power 6 joule per second. Now, it is joule per second. We have to convert it to electron volts. So 10 to the power 6 is divided by 1.6 10 to the power minus 19 joule per electron volt. And our result will come in electron volts per second. It comes to be 6.25 10 to the power 18 million electron volt per second. Now number of atoms disintegrated we have to find. So 6.25 into 10 to the power 18, it should be divided by 200 because energy produced per atom is 200. And that comes to be 3.125 into 10 to the power 16. So energy released per hour, that is 10 to the power 6. And we have multiplied 60 and 60, and mass decay per hour will be delta E over C square in accordance with the Einstein equation, and it is equal to 4 into 10 to the power minus 8 kilograms. And in the 12th question, a star initially has 10 to the power 40 neutrons. So there is a star and it has got a lot of neutrons, because stars normally follow the principle of fusion. So it is 1s2 nuclei are present. It produces energy via the process, that is the fusion process. 1h2 fuses with 1h2 and there is formation of 1h3 with 1 proton, or 1h2 plus 1h3 fuses together forming 2he4 with 1 neutron. If the average power radiated by the star is 10 to the power 16 watts, average power 10 to the power 16 watts, the neutron supply of the star is exhausted in a time of the order of. We have to find the order of time. So adding the two processes, that is 3 deuterium nuclei, and in the reactant side and in the product side, it is helium added to proton and neutron masses, and then we find the mass defect by taking the difference of reactants and the products, and the mass defect is found to be 0.0 26 AMU. When this is multiplied by 931, then we will get joules. So we will get 10 to the power 16 watts. 1 watt is 1 joule per second. So our number becomes 10 to the power 16 joule per second. The number of neutrons used in 1 second. So now in 1 second, how many neutrons are used? We have to divide 10 to the power 16 by another number, that is 0.026 into 931, as we have calculated above, and this whole number comes to be 7.75 into 10 to the power 27. Now the time in which that neutrons are supplied exhausted, the number of neutrons must be divided by the number of neutrons used in 1 second. So 10 to the power 40 is divided by 7.75 10 to the power 27 in accordance with the question, and the value becomes 1.3 10 to the power 12 seconds. So the order of the number is 10 to the power 12 seconds.